keep going on Brian's bio quickly. Funded by NASA, NOAA, Department of Energy, NSF, and the Office of Naval Research. Brian's work focuses on tides, internal gravity waves, mesoscale eddies, and the role of the oceans in weather and climate. Like I said, Brian actually founded the Coastal Ocean Environment Summer School in Nigeria and Ghana. That's going to be the topic of the talk on Tuesday. Sounds like a really interesting talk to go and listen to. And yeah, I guess I'm going to let Brian take over. I'm sort of running through the bio, looking at, there's other things I could tell you about Brian, but come along for lunch after the talk. And just for me to plan for that, just a quick show of hands, who's going to come along for lunch with Brian after the talk? Okay, 3, 6, about 12. Okay, thank you. I'll work out a venue and I'll announce it by the end of the talk. Brian, come on up.
Thanks. So can everyone hear me okay? And online as well, I hope. Yeah, so I'm going to talk about global ocean internal gravity wave modeling. Probably most of you know what that means, but if not, I'll define these things in a few slides. It's a frontier science problem with many applications for satellite missions, ocean mixing, and others. And the fund, as Matt already mentioned, funded by many agencies, including a few that aren't showing here. Some of these agencies don't want their logos shown. It's kind of weird, but that's not true for NOAA. I should have put NOAA up here. One of the perks of being a professor is you get to have sabbaticals. I spent my first sabbatical in France, really liked it. But my second sabbatical, I thought about going there again. And then I thought, why not see somewhere I've never been to? I've never been to Australia. So I'm here basing myself at ANU for a year. And this is part of my Let's Tour the Other Places tour. I was at UWA last week and I'll be at Hobart in a few weeks. All right, so that's a little bit of background. Okay, now right away, let's see, advancing the slide.
Yeah,
We can on the screen.
sometimes when it's recorded, it stops you doing things that you otherwise like to do. So I'm just gonna,
Just click it.
we might need to use this mouse. Let me see if I can get rid of that thing.
Or maybe I need to do that, okay.
Yeah, exactly. There we go. Oops, I've unshared your. Let's try and move this thing. Whereabouts is the slideshow again? Somewhere there.
Yeah, I'm more of a Mac person, so.
Yeah, same.
Yeah, on the right, there is a full screen.
Arrow.
Oh, yeah.
Okay.
Oh, there we go. All right, good.
We need to hide that little floating thing. Let me know and I can.
I can hide, yeah, probably figure that out. Hide floating.
That's it. Yeah.
Okay. All right, so here's one slide where someone else was kind of explaining the big thing that we did here. So I like to show that. So Richard Ray is the world's preeminent expert on analysis of tides from satellite altimetry. So this is how he explained the work that I'm going to show today. So tide modeling is kind of a separate thing from general circulation modeling. So ocean general circulation models, as we all know, you have the atmospheric forcing, the wind, the buoyancy forcing. That's the thing that matters the most for the ocean. But on a global scale, these kind of models, which we all know and love, tend to ignore tides, didn't have them in there. And on the other hand, tide models tend to just be tide models by themselves. You can do a lot of science with just pretending the ocean is a one-layer ocean, shallow water model, only tidal forcing. That's a traditional tide model, but that model doesn't have the other stuff, right? And so there was kind of this brick wall between tide modeling, where, you know, tides aren't being changed by weather and climate, and general circulation modeling didn't have the tides. So what we did, all these words in the title matter. Concurrent at the same time, simulation of eddying general circulation and tides in global ocean models. So this was the first paper published in 2010, where we had a high resolution model with tidal and atmospheric forcing at the same time. So remove this brick wall, and you know, the real world has all this stuff happening at once. So why not run it that way? I hope that's clear enough. So that's the main thing I'll talk about. Models where you put tides and atmospheric forcing in simultaneously. Oh, yeah. Okay. So My research group collaborates with a whole lot of groups around the world that put tides into general circulation models. I started with the US Navy, but some of you may know that Dmitry Menamenlis at NASA JPL has run this gigantic global 1/48th degree simulation. Same idea. He came after us, kind of inspired by us. And I'm not going to read all these off, but these are just efforts that I've collaborated with in some cases, just a little bit. I'll highlight one of them is here in Australia. So Callum Shakespeare, probably most of you know him, and Andy Hogg and Del Morrison. They hired a postdoc, Lu Wei Young, and she is inserting the tides into a MOM6 model that, as I understand it, is going to be like Australia's global high-res model. That's your go-to global high-resolution model. So they're putting the tides in there for all the reasons I'll talk about here. So if you're interested in review papers on this topic, the first one I wrote was with a whole bunch of co-authors, published as a book chapter in this book here. And then in my entire career, out of all the papers I've published, I've only published 2 sole author papers, and one of them was this review. I figured I'd put everyone else on this one, so this one I would just write as sole author. So these are some, and probably every 5 years I'll write another one, because this is just an emerging topic that we're at the center of. And then just, you know, another 5 years go by, we'll have another 50 papers that need to be reviewed, or well, exaggerating slightly. Okay, so in case you don't know the terminology, but you probably do, but that's always nice to get a review. Internal gravity waves are gravity waves that are internal to the ocean. So the largest displacement signals are well below the surface. So you can have density surfaces or isopycnals moving up and down by 50 to 100 meters. And so here's one of the first couple papers I was on in tides was led by a person you probably have heard of, Harper Simmons. He's better at graphics than me, so he drew this little thing here. So you can imagine, you know, the biology cares about this stuff because it's changing the temperature and bringing nutrients up and down and all that. So you have these isopycnals are moving up and down. So what about some motivating observational studies? It's always useful. The first evidence for radiation of coherent low vertical mode, you know, baroclinic modes have numbers associated with them. So the lower modes that have the largest horizontal scales and less vertical structure, those things propagate coherently. And that was seen in acoustic tomography by a very important paper by Brian Duchamp and others. But I'll show it in a minute, a slide where you also can see it in altimetry. So you can actually see these internal tides, which are internal waves of tidal frequency propagating around the ocean. You can see it in data, and in a minute I'll show some movies. So we see these things in altimetry data and other data. And another, of course, key thing that people care about that ties to kind of everything that oceanographers care about is that a lot of the tidal dissipation takes place in coastal areas. The tidal velocities are largest in coastal areas. But we now know that a significant fraction of the tidal dissipation takes place in the open ocean when you have tidal flow over rough topography that generates vertical motions. So those isopycnals move up and down because of that. And those are internal tides, internal gravity waves of tidal frequency. Those things can eventually turn over and break and cause mixing. And that mixing can affect the overturning circulation and carbon uptake and heat and all these things that, you know, that oceanographer, pretty much every oceanographer cares about. So here's the internal tides in altimetry, this very famous paper by Ray and Mitchum, same Richard Ray who made that slide I showed earlier. So this is looking at a particular altimeter track with this number, and it's in the Pacific Ocean and it's going near Hawaii. And it's showing the amplitude of the M2 tide along that track. So M2 stands for moon twice daily. So it's the principal lunar semi-diurnal tide. It's the biggest tidal constituent out there caused by the gravity of the moon. And you see that there's this large scale envelope. So that's the large scale or barotropic tides. I'll show movies of that in a second so you get a better picture of that. But again, that stuff flowing over topography causes baroclinic motions, which therefore have a much smaller horizontal scale because they're baroclinic. And that's all this stuff here. So this is the sea surface signature of internal tides. So you can see the scale here is centimeters. So these peak to trough, these signals of the internal tides in sea surface site can be 5 centimeters, but down at say several hundred meters, that can translate to a displacement signal of perhaps 50 to 100 meters. So they're much larger displacement signals at depth. The important thing about the sea surface site signal is that you can see it globally in altimetry data. So you can use that to map them. That's pretty important. Okay, so now I'm going to show some animations. This is how I tend to do these talks. I just bring it back to that pretty easily. It's here, yeah. So it's helpful, I think, at this point to show animation. So this is an animation that was made when I was a postdoc at GFDL, first getting into all this tidal stuff. I didn't do any tidal stuff as a PhD student at all. One lecture by Carl Wunsch, that's all I had. Oh, okay. I have to figure out how to loop that. We'll know how
In
to.
the video,
We're at the bottom.
video loop, maybe.
It's just one of those squares at the bottom. There's one that's sort of like an arrow on top of an
An arrow on
arrow.
top.
5 or 6 along.
Alright,
Yeah.
yeah.
Thank you. Yeah, so as a grad student, I studied mesoscale eddies, which continues to be an interest of mine, but then I got into tides as a postdoc. And maybe I should just freeze it. So this is a movie made from our first global internal tide simulations, first global ones ever done when I was a postdoc 20 years ago. So it's a 20-year-old movie. And so on the left, you're seeing the M2 tidal heights. So these are these large blobs. So the blue is negative, that's a low tide. The red is a high tide. The tides do propagate. From your GFD courses, you know that Kelvin waves propagate this way in this hemisphere and that way in that hemisphere. You can actually see that. A kind of a fascinating thing in this hemisphere is look at New Zealand. New Zealand is a super interesting place for tides. Just point that out. Another thing, by the way, regionally of regional interest, look at the Northwest Australian shelf. Some of you may know some of the biggest tides in the world are up in that, near Broome. So as a tourist, I'm going to go to Broome for that reason to see the tides. That's most, you come to Australia as a tourist, you want to see the tides in Broome, right? So you have these large scale tides. So that picture I showed in altimetry, the large scale envelope, that's this stuff. So this is your tide that we're all familiar with. But what we're less familiar with in everyday life is that the tides flow over topography, causing vertical motions. The interfaces move up and down. That's the internal tides. That's this stuff here. So because it's a baroclinic motion, it has a much smaller horizontal scale, a much larger vertical scale. So the scale here changes by a factor of 10. This is only a quarter degree. Like I wouldn't even consider publishing a quarter degree simulation anymore these days. This is barely resolving these motions, but these are the internal waves that end up breaking. Okay, the next movie I want to show, this is just to make a point for young people. So I wrote this paper, Arbic, Garner, Hallberg, Simmons. It's maybe my 4th highest cited paper, so pretty good. But Simmons, Hallberg, Arbic is one of my most cited papers, and I'm not saying his movie is the only reason, but it was a reason. So you will probably agree with me that this is a better movie. So he made this movie. It's a more attractive color scheme. It shows the stuff growing from zero, instead of it's already spun up, which is what I did. And people in the ocean, in the internal wave community saw this movie and they thought, holy cow, it's the first time they saw these waves are really propagating everywhere. So in the internal wave community, this is a pretty well-known movie, and I'm on the paper, so I'm happy, but this is the paper that got cited more. So I'm trying to say something, right? Make a nice movie for your helps. Okay, so This has nothing to do with the talk today, but I'm gonna just, since I'm here showing movies, I'm gonna show you a fun thing that I got involved in. So, I'm the only physical oceanography in the history of my department. It's a broad earth science department. So the disadvantage is I don't have internal wave experts down the hall I can talk to. The advantage is you get pulled into these truly crazy and interesting side projects. So what happened here was you're in a broader science department that includes people that drill sediment cores. And they look at the history of the earth. And he said, you know, that asteroid that killed the dinosaurs must have made a huge tsunami. So we modeled it. And you can't resist that, right? So it took us a year to figure out the correct way to do the initial condition. And the correct way to do the initial condition is to find someone else who knows how to do it properly. And that person is a co-author. So there are people that make a living modeling asteroid impacts. That's what they do. So that's the asteroid that killed the dinosaurs. That's water, sediment, land. There's some foreshadowing here with the vertical axis. It's going to get real crazy in just a second. So this is what happened. Oops, crap. Why did that die? Here we go. So you see that just mere seconds after that asteroid hit, there was a hole in the earth 20 kilometers or more deep. Stuff was thrown into the sky. In some versions of this model, you actually see the ocean up in the sky. There's like the ocean's up there. And then this wedge action happens and you kind of create this wave. And then, so the main creation of the wave is this wedging action, that they call that a rim wave. Then you get material falling down from the sky and you get splash waves that are miles high. And then about, 10 minutes into this, you have something that we oceanographers can handle,
Why is your ocean so thin, like not 5 kilometers or so?
And I think this was 3 kilometers. So it gets in, well, where it hit in Yucatan, Mexico, actually in very shallow water. And so we did simulations with 1 kilometer, 2 kilometers, to just make sure it doesn't matter too much. What really matters is that farther away from the impact, the ocean was deeper in the Gulf of Mexico. So this is called a rim wave, and then you axisymmetrize that and plop it into a shallow water model. That's the kind of stuff we know how to do. And most of the energy of that tsunami was caused by the rim wave, but some of it was caused by the way, there's this gigantic crater, which they can go to and drill into and see, yes, it's there, and this is how big it is, and that shows that the models make sense. And there's a backwash into that crater. So about 10% of the energy of the tsunami came from that crater collapse. I just have one more movie. So then you take that initial condition that sort of actually symmetrize that 10-minute signal, then you put it in a shallow water model and you get this. So one thing about that, just real quick, is that
Was the Panama Canal not closed yet?
the Panama Canal is not closed, and that's critical for this part of the world because that allowed a major part of the signal to hit Australia and New Zealand. So I have 2 collaborators from New Zealand. I've never met them in person, but I will when I go to New Zealand as a tourist, hang out with them because I want them to show me the rock formations that they are convinced are tsunami upheaval, And part of the problem too is you have to have, someone has to make a map. What did the world look like 66 million years ago? And that's all, one of the New Zealand guys, he's doing that too. Okay, so that's just fun, while I'm showing movies and relevant to this part of the world and trying to figure out how to make this go back to full screen. This one?
Where
Highest square.
Oh yeah, thank you.
you can wear all.
Oh yeah, that one, right? Okay, so back to the main topic. So why would you add tides to high resolution models? So again, the tidal flow creates internal tides. So one thing is that these internal tides now propagate in an environment where the stratification is changing because you have a general circulation model. So you have seasonal changes, you have mesoscale eddies, and all those changes actually make the tide less predictable. So the tide is kind of one of those things you might think of as an inherently predictable motion. You know, tide tables, they tell you when the high tide is and the strong tidal currents, the ebb and flood currents. But the internal tides, because they move more slowly in a smaller spatial scales, they interact with mesoscale eddies and they get shifted around. So they're actually not as predictable. So we call that an incoherence. Some people use the word non-stationarity. Some call it modulation or not phase locked. Whatever word you use, that stuff is less predictable. And our models can show that. Now, another thing that happens is that the wind creates near inertial waves, then you have internal tides. And if you have a model with enough high resolution vertically and horizontally, you can get some nonlinear interactions and they start creating waves at higher frequencies. So if you haven't heard of this, there's something called the Garrett-Monk spectrum. So the Garrett-Monk spectrum means that beyond the near inertial waves and the tidal waves, there's very high frequency internal waves. And those are created, people think, by non-interaction between the tides and the near inertial waves. And then you create these high frequency waves. And those high frequency waves eventually get to small enough scales where they turn over and break. So that's where the breaking takes place, giving you mixing that matters for lots of oceanography. So just the fact that these models have a continuum that people are starting to think, yeah, it sort of looks like what's in the real ocean was an achievement. And so we showed that for our Navy HICOM simulations, and then my friend Dimitri Menamenlis simulations, they showed the same thing shortly after that. So the endpoint of this cascade is mixing, and so that's maybe the thing people care about more than anything else. Like, global internal wave modeling is a bit of a niche thing, right? So why would most oceanographers care about? Because the endpoint is the mixing, and that drives everything that all oceanographers care about. So I'll get into that. Briefly, I'll just mention internal waves impact ocean acoustics. So the US Navy is interested in this because of anti-submarine warfare implications. Some of you may know that some of the largest internal tides in the world just happen to be in the spots that the US Navy cares the most about, like Taiwan, places like that. So this stuff matters for that reason. Another thing is, what if you're running a regional model? You want to have the internal wave activity correct in that regional model. Well, then you might want to think about using our model for boundary forcing, because if you have a regional model and you're only using the traditional barotropic tidal forcing at the boundary, you're only getting the large scale motions, then you're completely missing those waves that propagate. That's why I was showing you the movies. You see in the movies, the waves propagate long distances. So people are finding now, us and others, that if you have a regional model and you don't let the waves propagate in, then you're not going to get the right wave energy in that region. So that's another reason you might care about it. Now, here's another thing that is highly relevant to Australia. Well, maybe not Australia, but Antarctica. When you guys are some of the world's experts on it, Antarctica are in Australia. Like, for instance, Adele Morrison, for one example, and Matt. And so the tides interact with all aspects of the cryosphere. So sea ice, floating ice shells, the ice streams, they're all affected by tides. So that's another reason to put tides in a big Earth system model. That's yet another reason that we care about it. And then there's SWOT. So SWOT is the Surface Water Ocean Topography Mission. It's been up there for almost 2 years now. I actually saw the launch. It's kind of fun, the SpaceX thing really does go up and then comes back down and lands. It was kind of fun to see that. Anyway, so SWOT is measuring sea surface height in two-dimensional swaths as depicted here at higher resolution than traditional altimeters. Probably most of you have seen these things. Traditional altimeters give a sea surface height field that's kind of blocky. And with SWOT, you're seeing sea surface height fields that kind of look like this. So why do the models that we run matter for SWOT? They actually matter a lot for SWOT. The reason is this, that SWOT is measuring sea surface height at this kind of resolution. And when you go to finer scales, as I showed you earlier, so sorry, on larger scales, you get the blobby, big barotropic tides. And for years, the altimeter missions had to map those things on the one hand, which is valuable tidal information. But then they subtract them out so that you see everything. So a huge percentage of the sea surface height variance that the altimeter measures is actually tides. So on the one hand, tides are signal, we use the thing to map them. And on the other hand, you want to see all the other oceanographic motions, you have to subtract it out. Now that you're seeing stuff at really small scales, now you have to play the same game with internal tides. You have to map them as best you can and then subtract them out so you can see all the small scale non-tidal motion. So models like ours are kind of the crucial models that you could use to, like, how big is that signal and how much do we have to worry about it? And it's much less predictable and it's much smaller scale, much harder to model. So it's much more challenging than the traditional problem of the large scale tides. So that's okay. I already kind of said all that. So the models that I'm talking about here today were used really, really heavily in preparations for SWAT. Like it was basically our models that showed internal waves are going to matter. They're going to be there. You have to figure out how to subtract them out, map them, all that stuff. They learned all that from our models. You know, I would, not just they, but we as well. Okay, another quick point I want to make before I just kind of like blast through, like, here's a plot from this paper and this paper and this paper. It's kind of like that. So you can characterize the internal tide fields by showing that we have about the right energy. So most of the results we've published on are like that, like we have about the right energy. But also for those, I know Shane does data assimilation, probably some of the rest of you do too. You can also get to a higher bar than just about the right energy. As I'll show you in some of our data assimilative models, you can get the right wiggle in the right spot at the right time. And the reason is that if you use data assimilation in a forecast model, which HICOM is the US Navy forecast model. So it's assimilating nadir altimeter data that's been detided. They've taken all the tides out of it, including the internal tides as best they can. But when you assimilate that, it puts the eddies in the right spots and it gives you the right stratification. So if you have and we've already tuned the model to get the right large scale tides. So if you have the right large scale tides and bathymetry and stratification, then you're going to put the internal tides in exactly the right spot. Sorry, there's always an error, but pretty close to the right spot. And then you're going to have the modulating effect of the eddies as well. So the Navy model can actually capture all that stuff to some degree of accuracy. So starting with kind of you can see the patterns are about right. So I call that characterization. So here's the phase locked internal tides, the M2 sea surface height variance as measured in altimetry, that's in the bottom, and then as measured in HICOM here. So there's some subtleties I can talk about later if you want. There's a lot of subtleties. It actually matters how long of a model record you analyze. So basically, because things are not exactly statistically stationary, mesoscale eddies are shifting them around, and there's different ways to think about this, but you get a different answer for the amplitude and phase of the coherent tide if you analyze 1 month versus 1 year. And so, long story, you can kind of correct for that by using longer asymptotic analyses. But anyway, once you do that, you get variance in the model that's within a factor of 1 point something of what you see in the altimeter model. That's what these numbers here mean. So you've got about the right patterns and amplitudes. So notice, as I was saying earlier, the Western Pacific is very important. There's the Northwest Australian Shelf. Hawaii is the example Americans use because Americans always do that. But, Hawaii is a spot, French Polynesian Islands. Another hot spot is here in around Madagascar. Okay, so that's a map of the internal tides showing that it looks kind of like data. Now this one takes a little bit of time to explain. I'll try to do it as best I can. So this has to do with the stationarity of it. So what you do here is starting with this top plot. You use hourly output from the Navy HICOM simulations. you're at a grid point, you have a time series. And you can do a frequency spectrum, and you can say, all right, the tides are in this range, you integrate the variance. Then what you do is you do a least squares fitting to find how much of the tides are looking like amplitude cos omega t minus phase. In other words, that's predictable sine waves. You subtract those out, and then you look at the frequency spectra again. So then you've got how much of the tides are in there that are not predictable, and you take the ratio. So that's what we're showing here. So this is showing you how much the internal tides are not predictable by that methodology that I just explained. And it's using hourly data from HICOM, and you're using frequency spectrum. So why is there so much unpredictability, say, in the equatorial Pacific? And we think the reason is, as all of you know, in the equatorial Pacific, you have this gigantically energetic undercurrent, and it is just scrambling up the tides. So the tides propagate in there from French Polynesia, and then that huge equatorial undercurrent just scrambles it up. Makes it very, very incoherent. That's what we think is happening there.
Why wouldn't that be more of a jet-like zonal structure if it is that undercurrent?
Actually, that's a good point. I think it's partly that if you scramble it up right on the equator, then the stuff stays incoherent as it continues to propagate. But it may also be that everything I just said is a little overly simplistic, which I tend to do sometimes. Yeah. But you do see it in other equatorial basins too. Now, that's from hourly output from the model. Now, if you know anything about altimetry, one thing you'll know is it doesn't sample the same spot every hour. It's every 10 days. Now, internal waves have a dispersion relation, so that means that peak in frequency also shows up as a broader peak in wave number. So you don't have hourly sampling of the altimeter data. You can't do frequency spectra, but you can look at wave number spectra, and you can see the bump in wave number spectra, but it's much harder to deal with because the spatial scales of the internal waves are very similar to mesoscale eddies, which in most places in the world are way more powerful than the internal tides. So you have this giant background of mesoscale eddies that you kind of have to subtract out before you play the game in wave number space. So it's messier, but you can do it. And this is what you get if you apply that same analysis to wave number space analysis of altimeter data. So, you may disagree with me, but like qualitatively that, the near equatorial stuff is showing up. So we think we'll count that as a victory. And so this is what happens if you do the wave number analysis on hourly data. And this is what happens if you do the wave number analysis on 10-day model samples, so that you're treating it the same as altimetry. But the point is, the models seem to be saying there's a pattern of non-stationarity that's roughly similar. So that'll matter more in a minute. Well, actually around here. So this is one thing I was saying before, that most of the papers we've published on tides in these models have been forward models. So the Navy runs models in forward mode, and then they run it in a similar mode. And it's only in the last few years that we've started actually looking at the tides in the assimilative mode. And so that's what we have here. So we look at these hotspots here, same hotspots roughly that I showed before. Northwest Australia is there. This is the Hawaii box here. And along those altimeter tracks, if you look at amplitude times the sine of phase, so this is a way of combining amplitude and phase information of tides into one quantity. HICOM is in the blue, and the empirical analysis of the altimeter data itself is in red. And so you can see that they track pretty well. So I'm really proud of this result. So Richard Ray, the guru of tides, said 10 years ago, you will never be able to do that. Well, here we are. So Richard's a friend of mine. I just submitted a proposal the other day with his name on it, but it was a friendly challenge, right? And so look, you can do it. And so again, it's because you tune the barotropic tides to be reasonable. We know the bathymetry fairly well. The assimilation gives you the stratification, it gives you a better stratification than you get otherwise. And so you have all the ingredients to get this coherent internal tide right to this level of accuracy. So then another thing you can do is you can actually try to reduce variance from the altimeter records. That sounds like jargon, but basically the altimeter is measuring sea surface heights. That includes everything. But a little bit of that signal is the internal tide. And so if you use empirical models based on analysis of altimetry data itself to remove variance, you get this kind of pattern. So you're removing more variance from the places where the internal tides are strong. If you use our HICOM model, you do almost as well. That's the point there. And then there are advantages to using that. So this is too complicated a plot to explain all the details, but the gist of this thing, I'll just tell you, is that if you take a HICOM analysis over 3 years to remove variance from the altimeter record, you get an answer that's almost as good as you get using analysis of altimetry itself. But if you use an analysis of HICOM that's only 60 days long or something like that, you do better. And the reason for that, we think, is that in the real world on 30, 60, 90-day timescales, you have mesoscale eddies acting. That's kind of their decorrelation timescale. And they're scrambling the things up. But if you have a forecast system, you're assimilating where those eddies are. So you're getting some of those dynamics right. So you can actually remove more variance from the altimeter record using the HICOM forecast over short timescales that include the effects of the eddies than you can if you use a longer record where you're kind of averaging all that out. So this stuff really, really matters for altimetry. So the French people that are putting out the products for altimetry, they're really keen to get us to work with them to improve because again, if you're looking at the altimeter data and you don't care about the internal tides, you just want to get rid of them to as high a level as you can. And so this stuff matters for that reason. So that's what this plot here means. It would take a while to explain all the details. So now we're doing the same thing with SWOT. So we're showing that if what you care about in the SWOT records is to get rid of the internal tides, you can use HICOM in conjunction with just empirical analysis of the stuff itself. And you can do a better job using those things together than you can without HICOM. And it's because the altimeter data is only giving you data every 10 or 20 days so that you can only do a tidal analysis over really long time scales. And by then you've lost the demodulating effect of the eddies. But HICOM doesn't have that shortcoming. On the other hand, HICOM isn't, it's a model. So I'm not trying to say it's capturing everything. I hope that made a bit of sense. So that matters for people in that world. Okay, moving on to other things. Of course, we've compared our models to other observations. We've compared them to moorings, to drifters, and I'll show a few results on that and on boundary forcing applications to mixing. So sorry about this. This is how I tend to give this talk. It's like we publish 40 or 50 papers and I just summarize it with bullets and a few plots from each paper. So here's something about drifters. So I published a paper in 2022 where we built upon work that other people had done, and they were all co-authors on our next paper. But there's a global drifter data set, and you can take that drifter data set and divide it up into different frequency bands. You can look at low frequency flows, the tidal band, your inertial band, and so forth. And so this is a talk mostly about tides, but I'm going to start with this plot showing the low frequency band. So undrogued drifters are drifters that sit right at the sea surface, and they have some systematic errors due to the fact that you have, wind effects and wave effects. They're not tracking the flows exactly, and people spend careers studying these things. You can ask them about the details, but anyway, that's what you have for the flow right at the surface. They're called undrogued drifters. So we're comparing the undrogued drifters to the flow in one of our simulations right at the surface. And so we're taking zonal average. And so here's latitude, here's kinetic energy. This happens to be the low frequency band. And one of the things that I think is really interesting there is that if you look at the uncoupled ocean model, so this is an ocean model driven by 6 hourly winds, you can see that where the model is performing least well is actually on the equator or near the equator. But on the other hand, if you couple the model, so now you have a coupled ocean atmosphere model, you get this much improvement. So you move from green to there. So I'm not an expert on low frequency equator flows or on ocean atmosphere coupling, but I'm pretty fascinated by this, that there's this big jump here. And a quick digression on that, you may know that NASA is planning to launch a mission to measure sea surface currents. And so where the models are doing least well is on the equator, and currents are part of the air-sea interaction story. And the equator is one of the places where air-sea interaction matters the most. And so all this stuff is kind of coming together that, you can't estimate currents on the equator from altimetry because that requires you to assume geostrophy, which doesn't hold on the equator. And so this kind of stuff matters a lot for that other mission that I'm interested in a little bit, more in a little bit. In fact, they had a meeting for that mission last week and I missed it because I'm in Australia. So that's what happens at the surface. Then you can also look at drogue drifters, which are measuring flow at around 15 meters. And you get basically the same kind of result. So that's a comparison of these models with drifters in low frequency band. Now, when you look at the near inertial,
So for the previous slide, do you have like spatial plots for those equator regions? Are they?
I do.
in terms of-
Yeah, I don't know if I have them in this talk. Looks like I don't. But yes, I do.
So there's not really any reasons that explain the discrepancy, I guess.
My memory is it's kind of all equatorial regions are not doing well in the models. Yeah. Yeah. Well, that's a good question. Yeah. I mean, if you want to talk after the talk, dig it up. I just don't think I have it in this slide deck. So when you go to the near inertial band, which is closer to the band we're talking about today, there's another thing that happens. So the model by itself sits down here, but when you couple it, you go way up to here, and then the real data is here. So I'm pretty sure that most people that run coupled ocean atmosphere models are interested in other things than near inertial waves. But a side benefit of doing the coupling is that because you're either clamping the ocean to the atmosphere, forcing a lot more frequently, you actually get a much better near inertial field. So people have known for a while that to get the right near inertial fields, you have to have frequent forcing. Well, one way to do that is just couple them. Then you're not dependent on NASA puts this product out every 3 hours or whatever. You just couple the models frequently and you get a better near inertial field. So side benefit of coupling, better near inertial fields. And then there's the tides here. So the drifters are Lagrangian things and the models are Eulerian. So there's ways to put seed drifters in the model and correct for the fact that you're doing a Lagrangian versus Eulerian comparison. That's what the gist of this red thing is here. So after making that conversion, that's this red plot. And HICOM, you can see, is matching that fairly well over most latitudes near the equator. Not so well in the Southern Ocean, not sure what's going on. I can tell you the mismatch between red and green here, highly embarrassing thing, but HICOM until recently has a numerical instability in the North Pacific, which is giving this crazy numerical stuff. It's not physical. So that's what's going on there. That has recently been fixed. So in future papers, this thing will go away. The MIT simulations are way up here, so they have too much tidal energy and HICOM's closer. So this is kind of a technical detail for specialists, but there's reasons why we think that is. My speculation is that you make the waves, but you don't break them. So if you don't break them, you have to have a knob to account for that. And if you don't have that knob, which this model doesn't, you're gonna have too much energy. Okay, that's maybe some detail you don't wanna know. So a little bit about boundary forcing, high resolution regional simulations. So I'm a little behind time here, so I have to go real fast. If you want to interpret the SWAT mission, which is very high resolution, you're going to want to run some regional simulations because you can't achieve really high resolutions in a global model. So we're doing some runs where we take the global model, boundary force a box, look at what's happening in the box, crank up the resolution. So MIT GCM coupled with itself is one simulation we're doing with Dick Peltier and others. And then we're working with the UCLA ROMS group as well on that problem. So for the MIT problem, we picked this box in Hawaii. And the gist here, just to go a little faster, is that this is a frequency spectra of kinetic energy at a particular depth. And if you look at running the either the global model or the regional model at resolutions comparable to the global model, you're way down here. But if you increase the resolution in your regional model, you go up to here. And the Garrett-Monk spectrum, this thing handed down from on high for 50 years, predicts a fall off kind of like this dash line here. So the regional model is closer to it has a lot more energy and is closer to expectation. So you can get a better internal wave spectrum in the regional model. And for those who know these things, you can also show that these things satisfy the internal wave consistency relations, which is a proof that, they really are internal waves. That I'm not showing that, but it's in the paper. So we published a bunch of papers from that regional simulation. And sorry, I'm really going fast now. The gist of this paper here, this is kind of an interesting thing. So climate models use the KPP parameterization to do mixing in the upper ocean. Those were developed for models that don't resolve internal waves. So once you do resolve internal waves, you might want to actually turn off background component of KPP, because the background component of KPP, there's the parts of KPP that are looking at real shear that you have in the model. The background part is just saying that in the real ocean, there's internal waves that break and we don't resolve those. So we have to put something in there. But now you have models that are resolving them. So you actually want to turn it off. And if you turn it off, then your vertical wave number spectrum, so that's measuring structure in the vertical direction, goes from the black to the blue, and the blue is much closer to the observations here. So the gist of that there is that when you have a model that is so much higher resolution than models that were run 30 years ago, you actually want to start turning some of the knobs off. That's the point there. Now, it's too bad I don't have more time to dwell on this, but I talked about this plot with Trevor McDougall yesterday. Here's the gist of this plot. We're running these models now at very high resolutions. As I hope I've convinced you, the near inertial fields and the tidal fields kind of look approximately right in terms of their energy levels. If you have those lower mode structures and enough resolution to get some of the non-interactions, then you're driving cascades of energy down to small scales. How do the models handle that? Well, models have subgrid scale operators. They have viscosity operators acting on the grid scale, and they suck up that energy. So that is the model equivalent of epsilon, the DDT of kinetic energy due to internal waves. And if you compare that to fine scale inferences from observational data, that's what we have here. So starting with the good news, Kunze is one of the famous compilations of this. So this is dissipation by internal waves from applying what's called the fine scale parameterization. A lot of jargon here, sorry about that, but this is internal wave jargon. They apply the fine scale parameterization to observations, you get this gray curve. And then Frederica Pullman did the same thing from Argo floats. Eric Kunze used observational data that wasn't Argo floats. They're both kind of showing this pattern that if you look at the internal wave dissipation from 0 to 2000 meters, you can kind of see why I'm avoiding below that for now. But looking at the upper 2000 meters, it drops by more than an order of magnitude, and the models, it depends on the exact settings in the models, but you can kind of track that. So the point here is that at least in the upper 2,000 meters, I would argue from looking at plots like this, and you see roughly the same thing here, that you can essentially start to quasi simulate the mixing. You're not simulating the actual breaking waves because models are really far from that. But you're getting what the model wants to dissipate is actually like the observations in the vertical profile. So you can imagine a future where one approach to studying mixing in models is you just simulate it. You do need a lot of resolution. Now below that, we do less well, as you can see. These are log plots. And it does matter exactly what the resolution is and your subgrid scale operators and all that. And you can read the paper for those kind of details, but getting towards a future where you directly simulate this. I'll skip that, and I'm gonna skip comparison to SWOT. I mean, this is kind of, we are comparing these models to SWOT, so too bad I'm skipping that, but I'm kind of near the end. We are looking at the impact of climate change on tides. So of relevance to Australia here is that Antarctica is not very far away. One of the things that's happening with climate change is that the ice shelves are thinning. And as the ice shelves thin, that has a major impact on the global tidal system. So the global tidal system will actually shift way over here. The tide will be different by a centimeter because of the thinner ice shelves in Antarctica. Why does that matter? Because sea level is rising. That's one of the biggest impacts of climate change from an oceanography point of view. But on top of the mean sea level rise, you also have the tides. So you don't build cities above the mean sea level line, you build them above the high tide line. So if the tides are changing, that's kind of like maybe 10% effect on tide. Like it's the biggest effect, of course, is the mean sea level, but the tidal is, if you're doing risk projections for floods, the fact that the tides are changing is going to matter at some level, and they're going to change in part because of stuff happening. And the Los Alamos people completely screwed up the inputs. That's why there's no figure being shown here, but once it's fixed, I'll have a figure. Why would you not want to include tides in OGCMs? Well, if you care only about really long timescales, it's kind of a pain to have high frequency motions that you have to get rid of. On the other hand, real data has that too. And tides are not the only high frequency motions in nature. You also have the diurnal cycle. So I think everyone should put tides in the models, but they can be a pain to deal with. My summary is really short. Lots done, lots left to do.
Thanks, Brian. That was great. People online, drop questions in the chat. You could possibly unmute and we'll hear you. Any questions from the audience? Jan and then Gabby.
That's a great talk. Could you give us like a brief understanding of how the ice shelf thickness affects tides like a long way away? Like what's the mechanism?
Yeah, the reason is that when you're a tide modeler, like when I first became a tide modeler, I was really wowed by this. I didn't think of this, but you think of the ice shells as being rigid. Like I would have thought it's a rigid lid. It's not a rigid. The tides do this. And so from the point of view of just running let's say we're just running a one layer tide model, pretend that what you do is you take the water column depth from the seafloor to the underside of the L shape and you just run a model as if the ice shelves aren't there, but the water column thickness is to the underside of the ice shelf. And so if that thins, then it's like increasing the water column thickness. Do you see what I mean?
That affects like tides on the other side of the.
Yeah. So some of you probably heard of Chris Garrett, one of the masters of high frequency motions and tides. And he's written famous papers about tidal resonance. So he and I published a couple papers. I was telling Trevor yesterday, the hardest reviewer I've ever had is Chris Garrett as a co-author. Yeah. So it was fun and also challenging writing these papers. But anyway, what we did is we basically showed that, okay, the classical view of coastal tides is that you have this open ocean tide reservoir forcing the coastal tide, and if you have the right shape, you get resonance. You probably heard papers on that. Many people have. But what we showed is that because the coastal tides are so large in places like Bay of Fundy, Northwest Australia, there's actually a back effect. And so this is relevant partly for ice age tides. Like you go to the ice ages and suddenly you don't have those shelves anymore. So you can show with a model of coupled isolators that in the extreme case, if you just get rid of the coastal tides because sea level is so much lower, the open ocean tides can get much bigger as a result. So that's an extreme example showing that if you perturb the coastal tides, the open are bigger. So we're not talking about completely getting rid of the ice shelves or coastal areas, but there's enough of a perturbation that the coastal tides are actually back effect. So this thing in Antarctica, I think it's an example of that back effect. You're perturbing it. The Antarctic tides are very important. They're very big tides in Antarctica, and they cover a big area. And the Southern Ocean is at the center of the universe for a lot of things. I wouldn't say it's the center of the tidal universe, but it does matter. So it has a long-term ripple effect.
Easy question. When you were comparing low resolution versus high resolution models, high resolution, how large, how high
You
are
mean the regional modeling?
Oh.
So, oh yeah, I didn't mention, well, it's in the slides, but I went through it so fast. In the case of the MIT ones, yeah, this is worth a detail. So we're taking global 1/48 90 level simulations. And inside the patch, we're increasing the horizontal resolutions by factors of 8 in X and Y. And we triple the vertical resolution.
Okay.
And that's what we happen to do in that case. Now, in this HICOM ROMS thing, we're down to 600 meters horizontally and more levels. I don't remember the exact thing. This one hasn't been going on quite as long. But it is very important because this one we're running the high resolution ROM simulation exactly in the spot where the SWAT calibration validation is centered, which is off the coast of California.
below 1K?
Below 1K, and we have, we are, one of my former postdocs, Rita Brada Thakur, who's now back in India as a faculty member at IIT New Delhi, very proud of him for that. But he's continuing to work with us on comparing the high res simulations to the SWAT moorings.
Right, quick one. Do you have any comment on the plethora of tidal mixing parameterizations to include in models?
Yeah.
So shortcut, not explicitly resolved tides, but do you have any comment on those? We've tried them a couple of times and they've sometimes created weird
Well,
flows.
I mean, you can see because I love these, like, because I'm American, I guess, like the biggest computers, the biggest model. So, we're going to try to directly simulate the models, but obviously climate model scale, this approach isn't going to work for a while. So like Harper Simmons et al. Is one of them probably that you're using, right? And Kurt Olsen's worked on some. I mean, to be honest, I wasn't on any of those papers. I'm not really an expert, but
Yeah, so I mean, but you see that field going, progressing and doing
yeah,
a half decent job at those, yeah.
I think Kirk, I did my postdoc at GFDL and I had lunch with Kurt Bryan. So, not me and him, but like a whole group. Suki Manabe was in that group too, the guy that won the Nobel Prize. Like we just all go to lunch and there's Suki and Kurt. And, Kirk, the Manabe, Lewis and I forget who.
Ryan and Lewis.
Ryan and Lewis, yeah. So, that they just, here's what we think the mixing profile is. It's a good place to start. I think Simmons et al. Is better than that because what they do is they're taking the output from a barotropic and they say, here's what the dissipation is. They assume a vertical profile. So it's going to be enhanced in regions where there is strong topography. I think it's definitely a step in the right direction. And then other people have refined it, Angelique Malay, Kurt Olsen and others. I'm not really, I don't know if I can say much more than that, but
Yeah.
I think our approach, 100 years from now might be the way we just simulate it, but these kind of simulations, you want to do a 100-year climate run. But someday we'll get there. That's what ours is in that spirit. Like someday we'll do it this way.
It's a good test bed for the parameterizations as well to see how they.
Yeah.
Okay, look, thanks, Brian. Great talk. We have lunch downstairs. I'm thinking, we chatted before, you know, the lounge is just too formal a setting. So we're gonna go down to the library lawn here. There's a cafe. And if we all queue together, I will get your lunch. And we can just sit at one of the tables there and continue the conversation
That sounds.
over lunch break. Everybody online, thanks for joining. Brian, thanks again. Great talk.
Thank you.